Ladies and gentlemen, friends, colleagues, I'm extremely happy to welcome you to this Australian ICPEAC. We have a great tradition of ICPEAC opening with students' tutorials. We have distinguished lecturers for today's sessions, and I'm sure you will be enlightened and entertained. And let me please introduce the chair of the first session, Alicia Palacios, and she will take over. Thank you.
So good afternoon, everybody. We have now two 50-minute lecture with 10 minutes for questions. And now let me introduce the first speaker, is Barry Schneider from National Institute for Standards and Technology. He's basically the ideal person to talk about 45 years of computational atomic and molecular physics. So let me just introduce briefly who is Barry. He got his PhD in University of Chicago, then he moved in Southern California, General Telephone Electronic Laboratory, and in '72 he moved to Los Alamos National Laboratory, where he stayed almost 20 years. Until then he moved where he spent another long part of his career, most part of his career, in the National Science Foundation. And since 2014, he became a staff scientist in NIST. And okay, let's hope for a nice talk. So please.
Thank you. Yeah, it's great to be here because I've never been in the country before, and also I'm getting to see a lot of people who I haven't seen in a long, long time. So what I'm going to do is I'm going to try to give you a bit of an overview of a long history, 45 years worth, of computational atomic and molecular physics. When I initially gave the title of the talk, I said we, and I realized it's presumptuous to say we, so I put in parentheses I, because in fact, I'm not going to be able to cover everything that's been done. This talk is going to reflect my own personal opinions, and so from the very beginning, you know, I state that up front. And if I left out your favorite subject, I apologize. So, this is our favorite equation, the Schrödinger equation, both in time-independent and time-dependent form. The interactions here are, you all know these are simple. They were known in 1927 and 30. They were formulated. They were all electrostatic interactions. And even in the presence of a field, it's still basically the same. Even when you put in relativity and all the other bells and whistles, there isn't much of a change. So that's the set of equations we have to deal with. And I came across this little quote, which I put up here from Wigner, who mentions wonderful, I guess his idea here was that mathematics seems to describe the physical world in a way which we don't really understand why it does it, but it does. And it seems to be over and over again that mathematics can encapsulate a lot of physics and the equations. So that's okay, but I want to ask another question about how do we go beyond this to uncover, you know, maybe new or previously overlooked physics. I mean, the equations we were looking at before, they're pretty simple. Those interactions are simple. But what emerges in many cases is a very complicated and complex thing. So that's my motivation, the complexity of extracting and understanding how nature behaves from these equations has increasingly depended upon our ability to do, let's say, more and more or more precise computations. And what I'm going to be talking about is quantum phenomena like resonant scattering, resonant energies, whiffs and scattering, photoabsorption, angular distributions, and excitation and ionization. And so at the end of my talk, I'm going to talk a bit about multiphoton ionization in intense or ultra-short electromagnetic fields, and try to demonstrate how what we learned in scattering can be used there as well. Just for, So what's the real problem here? Compared to bound states, in a bound state, it's pretty easy. The wave function decays at infinity. In the problems we're going to look at, which are dominated by either one or more continua, I mean, they're very challenging because, I mean, in some senses, I'm saying it this way, but you can look at it in many ways. There are many branch cuts in this problem, and how you approach the positive real axis from the complex plane is crucially dependent on the boundary conditions, and we have to figure out how to do that right. You cannot ignore the branch cuts in scattering as much as you would like to. Well, there's a simple one, which is the square root of z, and you can see the 2 branch points. I just kind of throwing it out front. And of course, in the end, we want to make sure that the new and emerging generation of physicists can profit from what we've learned. So the focus for the first part is going to be on time-independent scattering, resonances, shape and Festbach resonances. I'm going to talk about the early days of stabilization and complex scaling and equivalent quadrature. This goes back to the late 60s, very early 70s. The R matrix and J matrix methods. I'm sure a lot of people know about the R matrix method. I don't know how many people know about the J matrix method. You can all raise your hands and tell me if you know about it. And I'm going to then talk about the complex cone. Finally, in the end of the talk, I'll get into the time-dependent problem, looking at propagating the time-dependent Schrödinger equation, essentially time-dependent configuration interaction. And there, what's really, I think, really cool about what's going on in the field is that we've got these ultra-short pulses that can actually control the electrons and make them do things that they couldn't do before, so we can steer the electrons to essentially, and control them to essentially make certain processes happen which wouldn't happen otherwise, or enhance certain processes, and it's just a very interesting field. Okay. So I'm going to go back first to very early days. So this is a slide which shows one of the early synchrotron images that came actually at the National Bureau of Standards, and this is helium. And these folks see in this spectrum, they see these, in an otherwise continuous background, they see these sharp features, and the question is, what are these features? Similarly, in H minus, you can also see this is from, this was, I believe this experiment is from the LINAC at Los Alamos. There was a LINAC at Los Alamos at one point. I believe the experimental work was done there. The theory is Bill Reinhardt's. And you see these sharp lines again appearing in the spectrum. And, you know, what are these? Okay. Well, here again, a totally different process. This is electron scattering from N2. And here again, we see these sharp features in otherwise a smooth background. So what are these? Well, of course, they're temporarily bound states of the system. And the electron gets trapped either in a barrier or it gets trapped from some excited state potential, and it sits around there for a while, and it gives these large peaks. So these are resonances, and people became very interested in applying numerical methods in the very early 60s to look at these. The first thing that they did was they wrote down for atoms a set of coupled simple 1D radial equations and numerically integrated them, extracted the phase shifts, took the phase shifts, and calculated the cross sections. In fact, if I remember correctly, it was the case, and I could be wrong on this, but it was the case that I think Phil Burke actually discovered the resonances in hydrogen numerically before they were discovered experimentally. And I could be wrong about that, but I seem to think that that's the case. But solving coupled 1D equations to extract phase shifts it's difficult enough for atoms. It gets very, very difficult for molecules. So chemists, mostly chemists, began to think, well, can we cheat? Can we somehow modify the bound state methods that we've been using to do quantum chemistry, let's say, to do scattering problems? Carefully, and we'll see what I mean by carefully, carefully taking the limit as you come down on the real axis. So one could think of doing a simple computational experiment. Let's just take a scattering wave function and expand it in a set of L-squared functions. And if you look at that and you disregard the overall, look at the shape, normalize them approximately to one another, you will see that they actually look pretty much the same out to a point in space where, of course, the basis set dies and you won't see that. You'll see it'll die off and the real scattering wave function oscillates. So people began to ask, particularly Howard Taylor, who incidentally was my postdoctoral advisor, he first began to ask questions as, can you just use simple bound state ideas directly to predict where resonances lie? And that was called the stabilization method, and I'll tell you a little bit more about it in a minute. Other people about the same time, Rick Heller, Hashim Yamani, Bill Reinhardt, actually four of these people were Bill Reinhardt's students. And so he produced some very good students in the time that he was at Harvard. So Howard asked that question, and what he found was, and I'll show you this, is that if you look, there's a plot from one of his papers of the scattering wave functions versus the expansion in a set of square interval functions out to some point. And Howard asked, could you possibly predict from doing these bound state calculations the energies of the resonance? And lo and behold, it is true you can. It turns out that for these particular eigenvalues, they stabilize as the basis set gets larger and larger. And so Howard was saying, I'm making no attempt to tell you anything about the width of these or the phase shifts, but I can tell you where you should look for the resonances. And he was able to do this with these quantum chemistry codes for fairly complex systems. And he would tell the experiment, he would basically say to the experimenters, take a look here and you may see a resonance. And so it was quite a good symbiosis between him and the experimentalists. It worked very well. But it's not a complete approach. It's very intuitive, but it sort of stimulated a lot of thinking. And Frank Harris and Bob Nesbitt sort of took off on some of these ideas, and they figured out ways to take the wave functions that came out and actually calculate the phase shifts from them. So Howard, as I said, was my postdoctoral advisor, and more than my postdoctoral advisor, he was my dearest friend for a long, long time. And he passed away a couple of years ago. He just a swell guy and just a wonderful person. So I miss him a lot. So here's another idea that sort of came up at that very time. It's maybe an odd idea. It's the idea of complex rotation. So you can say, well, what if you replace the radial coordinate by r times a complex value? What happens? Well, a mathematician named Barry Simon did a lot of work on that, and he showed that if you do that, what happens is that the resonances get rotated into the lower half of the complex plane and get exposed. So instead of being immersed in this branch cut, they really come out and you can spot them. So can you use this as a computational approach? And the answer is you can, but there are some problems with it. People did it, they used it, but think about the fact that if you have to scale all the orbitals by some constant, theta, I theta, what happens to the inner orbitals in an atom, for example, where alpha is very large. Well, they oscillate like wild, and it's very hard to numerically calculate the integrals. So this wasn't the best approach. You could use it, but it was not optimal. There were some other problems. If you try to apply this complex scaling idea to molecules, the electron-nuclear interaction makes it impossible to just scale the electronic interaction in the Born-Oppenheimer approximation, and that's a big drawback. So what people thought about was, could we get around it? And one way to get around it was to use complex exponents. And this was more robust, and it worked. Following on that, essentially, I believe it was, well, I'm not sure who I can attribute the exterior complex scaling to. Certainly, Bill McCurdy and Tom Racino did a lot with it. Here, what you do is you just don't. You keep everything real up to a point. And then, at some R value, you rotate into the complex plane, either sharply or smoothly. If you do that, you can show you will be able to satisfy the scattering boundary conditions and produce outgoing waves as needed. Another idea that was floating around at the time was called equivalent quadrature. And here the question is somewhat similar again. So if you diagonalize the Hamiltonian in some square integral basis, how can you relate that to the true scattering wave functions? Well, what you do know is that if you take a matrix element between the resolvent and two other functions, and you use the true scattering functions, you can write that in terms of a quadrature, which looks like the second line there, with no error due to the branch cut. Basically, what you're doing is, in that expression, you're adding and subtracting a principal value integral, which you can do analytically, and the difference, which is right here, is not a principal value. So you can preserve the branch cut very nicely, but that's with the true continuum functions. What Reinhardt and his collaborators showed was that for certain simple Hamiltonians, like the free particle Hamiltonian or the Coulomb Hamiltonian, there were special basis sets, orthogonal functions, in which you could directly relate the normalization for the true continuum function to the normalization in this L squared basis. And that allowed them to actually take the limit of I epsilon going to 0 in a very stable way. They had tried other approaches too. What they did was, at one point, they would actually evaluate that resolvent for complex Z off the real axis, where the poles were not so violently manifesting themselves, and then they would analytically continue that back to the real axis, and they found that that was a highly unstable procedure in most cases, so they abandoned it. But I didn't say this, I'm going to say it now. If you can figure out this equivalent weight, then you can make the connection between the expansion in the L square set and the true continuum functions. 1 month ago, to show you 45 years is sometimes things happen, Bill Reinhardt actually started to look at this problem again. And he's now been able to come full circle, and he now knows how to calculate the weight functions for any arbitrary basis. And he's going to publish a manuscript on it. It's essentially a numerical procedure where he can use the weights of the quadrature to get the weight function at those points and then do a very stable interpolatory procedure. So wait, you'll see this paper or papers coming out soon. So I would say what we learned from all of this is that bound state techniques, suitably modified, can be used to do scattering, to get scattering information. And the original measures provided insight, but perhaps with the exception of ECS, were kind of clumsy. And but the most important point is the real complication of scattering, of the scattering boundary conditions, really only needs to be faced at long range, where in many cases the physics becomes simpler, because the electron's going away from the other electrons. It's not so tied up with correlation and exchange. It's in a region dominated by multipolar forces. So how do we effectively combine these ideas, bound state ideas at short range with other techniques at long range to extract the scattering information? So when all this stuff was going on in the US, the people in the UK were not sitting around. They knew about the Wigner's R matrix idea in nuclear physics. And in nuclear physics, the R matrix is not used as a computational tool, basically. It's used as a semi-empirical approach to try to find the compound resonances in nuclei. But, you know, Phil said, well, you know, why can't this be a computational technique? If we can do the problem inside this radius, okay, imposing some boundary conditions which make it look like a bound state problem, can we just take that information and do something on the surface of the sphere to take into account the long-range interactions and have a complete computational approach? So that's what they did, and I'm going to sketch that. So this is not the way they derived the theory originally. The way I'm doing it here is I'm doing it by adding, I wish I had a pointer, but I can. I'm adding and subtracting a surface operator called L, which is called the block operator. And what happens when you do that, of course you're adding and subtracting, so it doesn't change the equation. But now the operator, this operator here, is now, for real B, if B is chosen real, is now Hermitian, whereas the original operator wasn't. Does it work? Okay. So once we do that, we now have essentially a bound state problem inside the sphere. The added value of doing the derivation this way, which perhaps wasn't obvious to everyone originally, was that if you treat this problem as a variational problem, you now no longer have to fix the derivative of the basis set on the boundary to be a value. You can use basis functions which have arbitrary derivatives. And that improves the convergence a lot. But more importantly, it makes the method really applicable to molecules, which the original approach would not have been. So to summarize, I mean, we saw this, we applied it. The block operator ensures the hermiticity and acceleration of convergence and allowed us to do molecular calculations. And in fact, I should say this, but the first R matrix calculation on molecules preceded Burke's work by 2 years. And I had done it by adapting these bound state programs to do it. Okay. So I said that already. Diagonalize at fixed internuclear distances. Get the potential curves. And if you want to look at the full theory, you can do it this way. You can say that what you've got is a piece of the wave function called P, which contains all the asymptotic information, all the breakup processes that you need to look at infinity, and then a bunch of square interval functions which can be chosen in any way you want. And of course, all your bound state intuition can be used here. So if you insert that set of bound state R matrix levels in there, you get an expression like this for the scattering wave function. You project it onto the channels, and you get a matching. Now, isn't that actually kind of nice and beautiful? I mean, here you have this R matrix, which you calculate these wave functions one time, and then you're able to set this R matrix up for any energy. So you do one big, essentially large computational job, get the R matrix levels, and then you can, the R matrix eigenstates, and then you can set this up for any energy, and then all you have to do, all small a, is match. So if you know what the channel wave function looks like on the surface, you can plug it in, and you can extract the scattering information. If you don't know what it is, you can take this R matrix that you got, and you can actually propagate it out to larger distances, where you do finally know what the asymptotic form is. And that's called R matrix propagation. I won't talk about it. Anyway, I think it's a beautiful approach. I don't know whether Chris is going to mention this in his talk. I hope he does, but there are connections between this and quantum defect theory. So let's hope maybe Chris will do that. Some quick remarks. The basis sets have to be Gaussians for polyatomic molecules. You just simply can't do the integrals otherwise. The integrals only occur over a finite region, so you have to subtract the tails, because in normal quantum chemistry, the integrals are done to infinity, and you can do lots of analytics with that. Here, you can do the integral to infinity, but you've got to subtract the tail. It's doable. I mentioned this already. A single diagonalization gives the full scattering K matrix at any energies. And that's, of course, nice if you're exploring for resonances, because you can do a very quick scan. Just calculate the R matrix over and over again. It's a simple sum at each energy, and watch and see where the resonances occur. There's no need for complex rotation, complex basis functions, or any non-Hermitian mathematics or hocus pocus. It's all pretty easy and done in real space. The treatment of the external region depends on the nature of the problem. In some cases, you can just match the free waves. In other cases, if you know the multipolar forces outside, as I said, you take the multipolar form of the equations, you integrate inward, and you match. Okay. So, and last but not least, I said this implicitly, the internal and external dynamics are dominated by different physics, and in the inside you have to deal with all the complexities of correlation and exchange, but outside it's typically multipolar and much simpler, and you can exploit that in this approach. The J matrix method that Reinhardt developed is actually very similar. What Billner students found was, as I already said, is that the free particle Hamiltonian, not just the free particle Hamiltonian, actually the free particle Hamiltonian and the Coulomb Hamiltonian, there are orthogonal polynomials which can be used to expand the continuum solutions to that problem. And essentially exactly. So what you can do is you can essentially take the potential, take a subset of those, make a matrix representation of it. So you have a matrix like this, which is full, and then connect it up using this set of orthogonal functions, which turns out satisfy a three-term recursion. That's where the word, that's why they call it the J matrix for Jacobi matrix, because Jacobi matrix. The point is this microphone. Oh, sorry. I thought I was loud enough on once, but okay. So you can put this all together and get a very nice method, which I say is very much like an R matrix idea, but you can view it as an R matrix idea, but done in function space instead of real space. And it has connections up with the equivalent quadrature because it turns out that these basis sets that are used for the J matrix are actually the basis sets that provided the equivalent quadrature. And now we hope maybe we can go beyond that, at least Bill does. So far I've been talking about mostly fixed nuclei things or atoms. So what happens when the nuclei move? So one thing you can do, one simple thing you can do, is if you know the scattering amplitude at fixed r, you can simply say, let's take that amplitude, sandwich it between row vibrational wave functions, and use that to calculate the scattering amplitude over the row vibrational set. Does this work? Yeah, under certain circumstances. It works when the electron collision times are short compared to the nuclear motion. So the electron is not hanging around the other electrons much. It usually fails near thresholds because the electron energies are comparable to the nuclear energies. So you have to worry about it. It certainly doesn't describe the energetics and probably doesn't describe the dynamics either. And in a resonance where the electron comes in and hangs around a while, it's not clear what you should do. So let me just discuss two problems which were done. These are fixed nuclei problems in a sense, but they were done as a function of the internuclear distance. So I use the word dueling resonances in H2. So this was a discovery that actually came about because, I can attribute this, maybe I should have known better, but I can attribute this directly to computation. So I was looking at these H2 states back in the early 80s. And I was doing these R-matrix calculations, and I was calculating the positions and the widths of the resonance. And I noticed that when I moved the internuclear distance just slightly, my resonant width changed dramatically. I thought that was a bug in my program. But when I began to look at it more closely, I realized it was not a bug at all. It was actually because there were two resonance series, this one and this one, which exist of singlet pi U symmetry. And if you do the curves, if you plot the potential curves of these doubly excited states, they cross. One of the curves has a very small width. One of the curves has a larger width. And so when they cross, the adiabatic curves show this dramatic change. And you can see that in this figure, right around this value of the internuclear distance, you see dramatic changes in the width. And so we actually submitted that to FISREV letters calling it dueling resonances, and they rejected that. They wouldn't let us use that. It became some not very interesting title, but anyway. So I think this is a direct case where really computation played a very important role in discovering something. In some sense, you have to know that this is going to happen because in the united atom limit, this has to go to the lowest resonance of helium, and you know what that width is. And so you have to realize after the fact maybe that it's got to change dramatically over that internuclear range of separations. Another problem that a bunch of us took up was, so we had all gotten to the point where people were confident that the codes that they had developed by various different methods all were working. And so what we wanted to do is do a test problem on a simple test problem. So we took the two-state close coupling in H2 of the ground state to the triplet B excited state as a test. And all of the three methods, which were R-matrix, linear algebraic, Schwinger, all went out and we computed it independently. We tried to use the same basis sets. And we all got results which were basically the same. Now, what had been done prior to that is that the scattering orbitals that were used in early calculations were orthogonalized to the bound state orbitals. But the terms were not put back to relax that orthogonality. It turns out that that's essential. If you don't put back those terms, you cannot hope to get the right results in this problem. And that was shown quite dramatically when we did the calculations both ways, and you can see that here. And that's another calculation. So this is ours without the inclusion of the orthogonality relaxing, and this is another person's calculation without including the orthogonality relaxings. Here's a comparison of theory and experiment. It's a pretty good comparison, except for these 2 points. We were suspicious that something might be wrong with the experiment, so we contacted the experimentalists, and they went back and looked, and they actually found out that they had missed a factor of 2 in their normalizations. So, which triumphs, theory or experiment? In this case, probably theory. So, I noticed a recent CCC paper on, I guess there's been a few CCC papers on electron H2 recently, I guess. And one of them noted that even with the best close coupling calculation that they did, which was something like, I'm sure these people are in the audience, 500 channels, does that sound right? Or more? Hello? They did not get results that looked like ours. They got a much sharper peak that was moved in. So even today, there seems to still be disagreement in this very simple problem of two-state, of excitation to the B triplet state in H2. So now what happens when the nuclei actually really do move? So we want to go beyond the adiabatic approximation. 15, I think we'll be okay. And so the question is, do you, whoops, what happened? Don't lean on your, let me stop the clock. My mouse disappeared. Oh, come on. That's what happened. I knocked the mouse off. Can you get back to me? Okay. Thanks.
It was already on the screen. No, it's not.
That's all right.
No, it's not on the screen.
Oh, that's funny. It's not on the screen, though. Yeah.
No, it's doing it here instead of there. Is this weird? No,
Yeah.
it's there.
Thank you. Appreciate it. So the question, I guess, was, do you need to completely couple the electronic and nuclear degrees of freedom in a non-adiabatic way? Stated a different way, can a Born-Oppenheimer treatment at short range be relaxed at long range to produce sensible results? And I felt at that point that the key answer was in the R matrix. And how to integrate that into the formalism was a goal I set. So what you can do is you can generalize the R matrix expansion to now include the vibrational parts. You get a modified R matrix equation, which has a block operator for both the nuclei and the electrons. You can, whoops, you can plug it in and get an equation for the vibrational wave function. And what's on the right-hand side are simply the surface terms that have vibrational excitation and dissociation. Notice in doing this, I did not include, and in fact I neglected, the coupling of the electronic wave function to the nuclear wave function via the nuclear kinetic energy operator. And you go through the mumbo jumbo of the algebra and you get an expression that looks like this. All I want to point out here is that if these surface amplitudes could be taken outside the integral, varying slowly with r, then what you would get here would be a Frank-Condon overlap between a vibrational wave function of the n electron system and a vibrational function of the n plus 1 electron system divided by an energy denominator. And what you would expect to see then would be peaks at those compound state energies. So we set out to do a first principles calculation on this. So we calculated the R matrix levels for the negative ion. The R matrix levels. I say negative ion, it's not a bound negative ion. And you can see that around 2 EVs, there's an R matrix curve which is shifted to the right and flatter. And this R matrix curve is simply because this electron is trapped in an antibonding orbital in N2. And when you crank through the numerics, what you get are all these peaks pretty well reproduced. If you start comparing it with experiment, the comparison is actually pretty good. Very good considering that this is a fully ab initio calculation which was done in 1980. But most importantly, since we had no adjustable parameters, we get what we get. So we get these cross-sections, absolute cross-sections. The experimental results, there were a set of experimental results, and it wasn't clear what the absolute cross-sections were, but we were able to say from our calculus what they should be, and there we go. So we were able to show which of the experiments was in fact right. So this is a summary, and I've said a lot of these things, and for many problems, you can do this, neglecting the coupling of the internuclear, the T sub r, the nuclear kinetic energy between the electronic levels, but not for all problems. And there are problems where you do have to take it into account. And you can look at some of Jonathan Tennyson's work where he describes how to do that. Okay, so now to the cone method. I am maybe going to run out of time, but we'll see. So in the cone method, again, it's the same idea. We expand the wave function in a set of bound state in a bound state part and a part which contains the continuum. We use the regular and irregular solutions to the asymptotic problem. We include them. This is a variational parameter in the problem. We stick that into the stationary principle that I had over there. We crank it through. It leads to a complex symmetric matrix. If you use outgoing wave boundary conditions, which doesn't suffer from pseudo-resonance problems. And we figured out ways to make certain matrix elements easy to calculate. You can put this again in a Feshbach-like formulation with an optical potential. You can run it through, and you finally get a T matrix expression from that vibrational wave, from that variational expression, which now is only in the stub space of the two free channel wave functions, which we then gives the stationary value of T. Okay. And you can compute this MQQ matrix using standard quantum chemistry ideas. So again, we're going back to the same thing. Use as much as you can of bound state lore and computation to make the scattering problem easier. Here's some results of, this is a calculation of, this one is acetylene. And you can see some resonance features in it. Or is that formaldehyde? Don't remember. But anyway, you can see some resonant features in there. And you can also see them in the experiment. And they occur. This was a fixed nucleus calculation, so they occur about at the same place. But there was no pretense here to say we were reproducing everything. In this problem, by the way, all these resonances are caused by pi star orbitals, which are the lowest unoccupied orbitals in these systems, which have very valence-like character to them and appear as these resonances. An interesting thing happens here in that at very low energy, the cross-section goes almost to zero. And that's what's known as a Ramsauer-Townsend effect in atoms. And it actually occurs even in molecules because at low enough energies, the cross-section is dominated by S waves. And in atoms, it is the S wave that produces the Ramsauer-Townsend. Okay, so what about impact ionization? So this is an even harder problem because now we have two continua. And it's a problem that has been around for many, many years and essentially not really been solved. So again, Bill McCurdy and Tom Rossino looked at solving this using the ideas of exterior complex scaling. And so what they did is they expanded the wave function to get a set of coupled PDEs. In the radial coordinates, they discretized it using finite differences, and they rotated at some large value. This led to a large set of complex algebraic equations, which were not particularly well conditioned, but they figured out how to deal with that numerically. And these were very big equations, about 1 million or so in size. But with ECS, you do satisfy the boundary conditions. They used flux ideas to calculate the cross-sections. Later on, they found better approaches. But the bottom line was they got really, really excellent agreement for many of these cross-sections between theory and experiment. So I would say this was a major computational coup. And they deserve a lot of credit for doing this. And it got in Science, which I guess meant that other people felt the same way. I do want to mention, I don't want to slight the convergent close coupling folks. They developed methods to do this, alternative formulations of the problem. I think the basic difference is that the ECS guys wanted to treat both electrons exactly equivalently, whereas in CCC, there is some inequivalency between the electrons. So now I'm really going to have to speed up. So I'm going to get to the last part, which is the time-dependent part. So here we work with wave packets, and we have to be careful about how we take limits if we want to compare with energy resolved calculations. There's a big advantage with wave packets. We can propagate in time and then project the wave function at large distances if we can propagate out far enough and on large enough grids. But if we can't do that, then we can combine some of these ideas with ECS and avoid this. And I think this guy over here has done, this guy in the red shirt has done some things like that too, right? So we began to investigate different basis sets. I don't want to go into too much detail on this, but this is called the discrete variable method. It uses a basis set, which is a set of Lagrange polynomials, which are defined at Gauss grid points. It's a powerful basis because it essentially allows you to make a very good approximation that local matrix elements are just the values at the grid points. And in fact, that's why I split this way, because it's both a grid and a basis. And we combine that, whoops, I'm doing this backwards. We combine that idea with dividing space into finite elements. And we use these basis sets in each of the elements, and then we choose a function which bridges between the elements. This leads to a sparse representation. It has spectral accuracy. We can compute the matrix elements easily from the submatrix elements. And to give you an idea in one dimension, it kind of looks like this, where there's zeros everywhere. So you can then take that, you can make the Hamiltonian up, you can time propagate it. In this case, we use the short iterative Lanczos, the Krylov basis, and my friend over there, Johannes, did a lot of this work, so I want to give him credit for it. We used it, and we used adaptive time stepping, and all that's involved is basically doing matrix vector multiplies and some scalar products. So it's very efficient. I'm not going to show this. Everybody knows this is the helium close-coupled equations. So here's the results of that. This is a result of the calculation of strong field, two-photon ionization in helium, both in the region where only correlation can cause these two electrons to come out, so they have to share their energies. And you can see that these calculations here, and one of which I think is Alicia's too, all pretty much agree. This one, I don't know. But I don't know what they have to do with these two calculations. You would think that was on another planet. But they were purporting to do the same calculation. Anyway, this rise at the threshold is where you can get sequential ionization. And this was studied further, and it's called virtual sequential ionization. Or is that the right terminology? But it's basically the fact that even below threshold, you feel the effect. Johannes wrote a very nice MPI code to do the calculations. This is a plot he made. He tried these on a bunch of supercomputers, and we found out, as we would like, that we got linear scaling, which is about the best you can do. So we felt we had done a pretty good job on this. And we learned some things. Most importantly, I think, we learned that some people may not have believed this, that if you propagate out far enough and for long enough times, you could actually project the asymptotic wave function onto free Coulomb waves. And there were people who said that that wouldn't work. But as Johannes showed, by doing this, he converged the interelectronic interaction matrix element to about 1%. So certainly you can do it. You might have to work hard, but it's doable. So, do I have no more minutes? Okay. Then I will stop. There's some interesting things in H2 plus involving two-slit diffraction phenomena, which I guess I can't talk about because I don't have time, but I can show that one curve here. And you can see these diffractions. And they're not at the classical angles until you get to very high energy. So attosecond physics has a lot to teach us. And I hope we'll be learning more and more. Thank you.
Thank you very much.
Well, I unfortunately prepared for an hour.
We have time for questions. Please wait for the microphone to reach you. So, we are open to comments. Anyone?
Chris?
Please.
Yeah, I'm.
I think it's on.
Hello.
Yep. I can hear you, but I don't think the mic's on.
Okay, I'll project my voice. I was wondering, this point you made about the non-orthogonality, you said the terms had to be put in. I mean, I understand, I think, a fair number of the issues in orthogonality, but I don't understand quite that
So it's easy. If you've orthogonalized the free waves, let's say to the sigma g and sigma u orbital, let's just say in that two-state closed coupling, there are going to be terms which look like 1 sigma g squared, 1 sigma u, or 1 sigma u, 1 sigma g, 1 sigma u squared, depending on the symmetry. The earlier calculations did not put those terms into the variational calculation. You cannot orthogonalize and not relax the orthogonality. That's a severe constraint on the scattering wave function.
So you subtract something from the basis, but it has to be put back in.
Yes, Bob Nesbitt called that transfer invariance, but it's got to be put back in. I think Alex wanted to answer. Go ahead.
No, he's the guy with the microphone.
Ah, okay. So no more questions? Okay. Everything was perfectly clear, right?
I do have a question. Okay.
Mm-hmm.
You have told this story about everything with one electron, or the most 2 electrons in the continuum.
Yep.
But also 2 active electrons the most, meaning
Yeah.
if you want to study something like the GDK, that is really 3 active
Yep.
electrons, can you use their matrix, or I know cannot really, but what's the limitation, or how will be the extension to the Curie methodologies to treat them?
I don't have any direct experience, so I can't answer that question, but I think it wouldn't be so easy to do.
Do you think it will be a standard, or how do you?
I mean, if you've got in case where you have like 3 electrons coming out, or 4,
Are they tractable?
I mean, in principle, you can write down the equations, but they're going to get huge to solve. You're going to have to make some approximations, I'm sure of it. But I don't have any direct experience with that.
Okay, some last question. I don't have any experience at all with the J matrix.
Mm-hmm.
Not with our matrix methods either, but at least I have read a lot. What's the real advantage of this change in space for the J matrix with respect to the R matrix methods?
I think the idea is basically the same, except you do the R matrix in configuration space, and you match up to the known external solutions. What the J matrix guys do is they match in a matrix sense to the known external solutions, because they know, for example, they know the expansion of sine, let's take the free particle, sine and cosine in these basis sets. They know the exact expansions. So they know the infinite tail. And they can fold it back